Okay, and so we're talking about the marks, and you can have 0D marks, which are the point. They are 0D in the sense they don't have any size, only has position and maybe color. And you can have 1D marks. So these are the lines, which has one dimension that you can change, which is the length. And you can have 2D marks, which are the areas. And as a result, you can have different shapes of the 2D marks area. So the example shown here are the quite and complex 2D marks. And finally, you can have 3D marks. These are the volumes. For example, you can use a 3D cube to represent each data items. Then you have not only the area, you can have volume as well to represent certain attributes. Okay. And then after that, we move on to the channels. And channels are, say, the different visual attributes or visual thing about the mark that you can change. And they are independent of the dimensionality. So it's not entirely independent in the sense you can change color and then that you can change, doesn't matter it's a shape or point or line. But you cannot change, say, the length of a mark if it's just 0D, which is a point. And so we showed some examples of marks and including position. So the position itself, including both X and Y position. You can change the color of the mark. These are different channels. You can change shape. So the shape only applies if you're at least a 2D mark, maybe 3D mark, this also applies, but you can't change shape for 1D or 0D. And you can change tilt and finally size. So here the size is used in a fairly general term. So length, area, and volume all treated as size. Okay, and we spend a little bit of time looking at different examples. So for these quite simple charts, we try to figure out what are the mark and what is the channel. We're not going to go through here again. And then we talk about different types for the channels, because some channels are good at representing quantitative values, where other channels are good at categorical values. So we have different types, and this is where we stopped last week. So this is when we talk about actually if ordering or ranking the different channels about based on the effectiveness. And so the first thing to know is, the attributes on the left are for the quantitative, or they call ordered attributes. So these are the numbers, and the one on the right is the list for the categorical attributes. And you can see the ordered, the top one is the best, that's what to say here, and the bottom one is the least effective ones, which are the worst in terms of representing. So that means, and for quantitative attributes, and the most effective one is position on common scales. So that means we have these two values you want to represent, and you can use X coordinates or Y coordinates in the sense it's similar. And the common scale means they start at the same point and say they represent the same amount of the value, the same length. So for example, maybe this represents 100 in this case, and this also represents 100 in this case. So that's the most effective one. And the next one is unaligned scales. So you still use the position, but the start point is not the same. So, and for this value, 0 is here, and for this value, 0 is here. We're going to see some examples quite soon later on. They are still using position, but the start point is not the same. So it's not as effective as this one, because the users or the readers have to mentally try to estimate the values of the length. Okay, and then after that, and the 1D lens is the third most effective one, and then it's tilt, size, depth, which is a 3D position, so that's how far away the point is from you in 3D. And then you have an luminance and the saturation of the color. So this is like a gray scale, how dark or how gray the color and the shade is. So it's almost like a black white and kind of photo. And this is how red, for example, the red is how saturated, how deep the color is. And these two are similar in terms of the performance, so they're the same. There's no obvious difference between these two. And finally, you can use curvature or volume to represent and some value. You can say if this bigger value is more curved, or if it's bigger value, you have a larger 3D volume or larger 3D marker. And these, again, has similar performance or the same performance. They are ranked the worst. And so actually, and for these ones, especially the last one, you probably want to avoid using in your visualization. So you try to avoid using and 3D volume or curved if you can. We'll explain that in a second why that's the case. Okay, so on this side is the different attributes, or sorry, the channels to represent quantitative values. So some of these overlaps, for example, the first one using spatial region. So it's also basically that means the positions of the items. For example, it shows 3 blocks. And it overlaps with this one here. And so you can use position to represent different values. And the second most effective one to show categorical attributes is using color, whereas we can also use color to show quantitative values, but that's not very good, quite down on the list. And the next one is using motion. So you can have the points moving in different ways, depends on which categories they are in. Say the points in the, or data points in the same category moving the same ways. And in this picture here, it just shows the simple example, we have only 2 categories or 2 groups. And then, so for one group, it doesn't move at all. So they're static. So these are these points here. And for the other group, it moves. So it's circles around it, moving like this. Obviously, can't really see here. That's one way to show. And finally, and you can have shape to represent categorical attributes. So you can say for furniture, it's a cross. For IT product, it's a circle. And then square and triangle for different type of categorical attributes. Okay. And again, so these are ordered by the effectiveness. The top one is most effective, and the bottom one is the least effective. And also, and what is not so explicit here is saying that you potentially can use some other attributes to show categorical attributes as well. For example, and you might use, say, lens to show categories. So you may see the short lens is one category, medium lens is second, and the long lens is the third. Okay, and that is not even listed here. That means it's less effective than anything listed here. So any visual channels not listed on the here, that means they are worse than anything that is listed here. Okay, let's go to next. Okay, and so basically, and the way we rank these channels and is based on their effectiveness and expressiveness. Okay, so these are 2 slightly different things. Okay, so for the effectiveness, so when you design your visualization and you want to use the best channels or the highest ranked channels and for your most important attributes. So first, you need to decide which attributes is most important. For example, if you want to understand the profit of the product, and there's many other things involved in the attributes involved as well, might be useful. For example, the name of the product, the category of the product. But if you're interested in the profitability, the most important attributes might be the profit. Okay, and once that's decided, you need to decide whether it's an quantitative attribute or categorical attributes. Obviously, in this case, price, it will be a quantitative attribute. And then you pick the most effective ones, will be this one to represent price. Okay. And then if you have a second attribute, in this case, maybe and that's the category of the product. Maybe that's what you're interested in terms of looking at how the profitability changes across categories. And then maybe this next most important attributes will be the category. Then you can try to pick another, so the most effective channel for category. Again, you had the first word that is a number or categorical value. Obviously, category is a categorical value. And you try to pick the most effective ones that is still available here. And in our examples, because we already used the position to present or represent price, so we can't use spatial region again for category. So maybe actually you potentially can still use a spatial region for category. And in that sense, and the profit would be, say, the X coordinates, and the spatial region will be the Y coordinates. So that gave you basically a bar chart. If you can. And if for some reason, say the spatial region is no longer available, and you can use color, which is the next most effective channels to represent that. Okay, and if you have any other attributes that you want to display, and you can just decide which is quantitative or categorical, and picks the next available, mostly highly ranked or most effective channels. Okay, and then the other one is called Expressiveness Principle. So that means to match channel and the data characteristics. So at least to make sure, and for the numbers, you use the quantitative channels, and for the categorical values, use the things on the right. Okay, and finally, we're going to have a quick look at the rankings and how do we come up with the rankings. And so actually 4 criteria we use. So again, as I mentioned, and this is not a 100% rule. So they are correct in most cases, but not always correct. So there is some flexibility. And in the coursework, you will need to justify and why the channels you picked to show is the most effective. And then in those cases, and you might not follow exactly the orders here, but you just need to justify why that's the case. Okay, and so let's just have a quick look of, say, how we decide these rankings. So why do we think the position is most effective and, say, the straight D shape is the worst or the least effective? Okay, so there are 4 aspects: and accuracy, discriminability, separability, and pop-out effects. And we're gonna discuss these and in order. Okay, and so accuracy means how the human can perceive the value from the visualization. Okay, and so basically, if I have 2 values, one is 10, the other is 20. So visually, I should be easily to tell the second one is twice the first one just by looking at it without knowing exactly the numbers. That means it's accurate. But if you can't do that, that means it's not very accurate. Okay, and so actually, and for different channels like position, lens, and other things, we actually do not always perceive the same way. Okay, and then this is actually what happens, and based on experiment people did. Okay, and so on the x-axis, we have they call the physical intensity. So that means the things you see. Actually, in this example here, it's not just the things you can see. For example, it includes the things you can feel as well, like electronic shock. So this is like the physical stimuli, and potentially you could use a sound as well, sound volume, for example, or the strength of the smell. Okay, so that's the physical intensity. And on this side, is the perceived sensation. That means when you look at or feel, let's just say look at, just for simplicity, because it's most of validation anyway. When you look at the validation, what do you think the value is? And so what you want to be is, say, the physical intensity matches your perceived sensation. So for example, if you want to present the value is 1, you want people to look at it and think it's 1. And if it's 2, you want to think it's 2. And sometimes if it's 2, people might think the actual value is a little bit higher, or sometimes the value is a little bit lower, depends on the channel you use. Okay, then that's why those channels becomes less accurate in representing the values. And then you can measure this. So you can use, let's say, area, and then you increase the area. Say area become 1, 2, 3, and 4, and 5, and you ask people to say, what do you think the area is? And then you can plot a line like this. So it actually what it tells you is when the area is 2, and what people say is something here. So the perceived size increase is about, or the size is about 1.4 or 1.5, something like that. And when it's 3, and its perceived value is about 2. So what happens here is, for area, this increases slower, sorry, and what you see is actually increases slower than the actual value. So for example, when the value is actual representing the value, the area is now 5, but you perceive about something like 3. So you have like a 0.7 factor. And then similar for depth. Depth is in 3D visualization. So the further away from you, the larger the value, it says the actual values you perceive is smaller than the real value. And the factor is about 0.67, and the brightness is even bigger difference, only 0.5, about half the value. And so if you show a value change, or the value of 5 in brightness, what people might perceive is something like 2.5. And so you can see, and on the diagonal is length. And so people's perception of the validation and actual value is quite well matched. So when it's 3, people most likely to see 3, and if it's 4, most likely to see 4. So that's why it's on the diagonal. So why it's a good one to represent and quantitative values. And so for this one, it says saturation. So that means how deep the color is. So people usually overestimate for the color. That means when the actual value just only, say, doubled from 1 to 2, people might think the change is about 3 times. and the ratio is
Sẽ đây
about
nó phải lon
1.6.
này rồi lon.
And then the last one is called an electroshock shock. So it's not really invalidation, and it's just included here as a example of extremely overestimation. So if you increase the electric voltage a little bit, for example, from 1 to 1.5, what you feel in terms of how painful that is might jump many times. Even actual voltage only changed maybe 50%. At 1, you may think it's about maybe 0.5, whereas if you go to 1.5, it's about like 3. So it's like 6 times difference when you feel. Okay, so obviously it's a not good way to represent the values, either acyclically or as an accuracy. Okay, and so let's do a test. Okay, so let's look at the saturation. So I'm gonna show you these 2 examples. So I'm gonna show you 2 blue colors, and one is darker than the first one, yeah? And then you have 3 options. So if you think the second one is 1.5 times darker than the first one, so please pick A. And if you think it's twice as dark as the first one, or twice as blue as the first one, pick B. And finally, if it's 2.5 times bluer than the first one, pick C. Okay, so we're gonna do a quick vote. And so for now, and if you think it's A, and please raise your hand. And 3 more seconds. I only have 2 people so far raise hand. Okay, so we have 3 people. Oh, sorry, 4 people now. Think it's about 1.5 times bluer than the first one. Yeah. Okay. Oh, got a 5. Anyone else? 6. Okay, 7 now. Okay, and can you all lower your hands? We're gonna go for the second option now. Can you all lower your hands? And so we're gonna go for the second option now. So how many of you think the second one is about twice as blue as the first one? Okay, so I remember we had about 7 for the A. Okay, and anyone else want to raise hands? So I have 14 so far. 15. Okay, so we have 15 who think it's about twice. Oh, oh. Okay, 17. So 7 and 7, oh, 18. Okay. Okay. Oh, and it's increased to 19 now. Okay. And then let's just do last one. Okay. So first, please, can everyone lower your hand? I'm just waiting for everyone to lower their hands. So you got a couple. Okay. And then now, can everyone who think the second color or second blue is about 2.5 times as blue as the first one, raise your hand. Do we have anyone else? Okay, So far we have 10. Okay. So we only have 10 for the last one. So we had 7 for the A, about 20, I think 19 for the B, and 10 for the last one. Okay. So the correct answer is actually B. So it's actually about twice. Okay, and I'm slightly surprised because previously we usually have more, and in C, okay, and then we're gonna do because based on the previous study, people tend to overestimate the saturation. Okay, and the next one I'm gonna do a bit differently. So I'm gonna maybe create a poll and maybe make it a bit faster rather than say go through one option by another. Okay, and the task is the same. We have these two lines, and then they have different lenses. So please don't cheat and to measure them, but just say based on your first impression. So is the second line 1.5 times or twice, or 2.5 times the length of the first one? Let me see if I can create a poll. So let's do. Okay, I'm just creating the poll now. Okay, and so you should see an option now. So you'll be allowed to choose between 1.5 times, twice, or 2.5 times. Okay, and so far I can see, you probably can't really see the progress, but from what I can see is about 74% people. Okay, one few more. Okay, so far I had 33 people, 35 voted, and 68% or 66% says 2, and 17 each, the 6 each, and says 1.5, and then 6 says 2.5. Okay, so actually it is correct. Say this one is actually twice the one of the first one. So majority of you get it right again. Okay. And so you should see the results now on your screen.
Yes, sir, we can.
Professor, you are on mute. Hello, Professor, you are mute. We can't hear you.
Sorry, yeah. I'm gonna move on to the last question now, and it's still the same task. We have these two and squares, and then one is larger than the second one is larger than the first one, and you need to pick and which one, how much the second one is larger than the first one. Is it 1.5 times, twice, or 2.5 times? Yeah, I'm gonna let you do the poll again, so you can pick. Ooh, okay, I'm gonna give it 30 seconds, yeah, to see if you can Okay, and 30 seconds is up. So I'm gonna end the poll now. Oh, there's still some people voting. Okay. Okay, and so can you see the results now? And so about half the people picked the first one, which is the most popular one, and it's about 18. And the slightly less people picked the second one, which is about twice the size, and that's 14, about 40%. And there's another 14 picked the 2.5, which is the least popular option. And again, the correct answer is actually 2. So it's actually twice the size of the first one. And you can see the majority of the people actually underestimate the actual value difference. So this is actually match what they seen before in the previous slides, if I go back. And so you can see here, say this line, the red line shows the area that it says when the physical intensity increase, like it doubles or 3 times the area, what people perceive is smaller. The change people perceive is a bit smaller. So in this case, even the second area is about twice the size, twice the area. It's actually exactly twice the area of the first one. That's you can easily calculate. But most people actually think it's about 50% more. So what you can see is, and this one is quite accurate. People can clearly see the second lens is twice the first one. At least the majority of people voted. Whereas this one, you underestimate. And actually this one, actually people tend to overestimate, where not the case in this one, in our experiment. Okay, and so that's the first and thing useful in terms of, and say which channel is good in terms of accuracy. It is people, how accurate can they estimate the values from the visualization. And the second one is, say, the discriminability, which is slightly a different matrix. Okay, put this one here. Okay, and so it says how many usable steps. Okay, so that means how many different values a channel can represent and the user can still easily see. Okay, and obviously the more the better. For example, if a channel can represent 10 different values and people can see easily, that's better than the value that can only represent 5 different values. And when it becomes 6, it becomes much harder to see. Okay, and here we're showing one attribute, or one channel, which actually is not that good. So the channel here we are using is the lens of the line width. So the line width, and so you can see this is a visualization of different countries in the Europe, and two are connected. And if there is trade between the two, so the thicker the line means there's more trade between the two countries. So you can see this is UK and this is Ireland. There's a fairly thick line connecting these. And this is UK and say this is Germany. And there's a fairly thick line as well. But for UK and Norway, they're connected, but the line is quite thin. So this is means there's much less trade between these two countries. Okay. I still have a few people and have their hands raised. Do you have any question or? Okay, so I assume there's no question. And raise your hand anytime if you have a question. Okay, and then the question here, back to the slides, is say you can use different line widths, but how many different levels can you see before it becomes harder to tell? and whether two lines are of similar width or different width. Okay, and in this case, in this particular visualization, and they only used 3. So, and for anything I think bigger than 500, it's 1 width. Between 500 and 250, the second width, the medium width, and finally anything below 250 will be the lowest one. So this is examples where you can't really use that much different levels. For example, if you look at these and say that 500 and 250 is already quite close. If you want to have anything in between 500 and 250, you might not be able to tell the difference. So especially when the two lines are not aligned next to each other. So imagine, say, and if you want to compare the width of this line between Greece and Germany, and let's say this line between Norway and Sweden, because they are not next to each other, it's quite difficult to tell and which one is thicker. Or I will say maybe Norway, but I'm not that sure. Or even maybe they are the same. Okay, so that means discriminability. If you can easily tell the difference, the more values, the better. But if you can't, that means it's not good. Obviously, the more different values you can easily see, the better. Okay, the next one is called separability. And so you want the visual channel to be independent from each other. But that's not always the case. And because sometimes one attribute can interfere or interact with another one. Okay. And what I meant is, for example, if you have 3 attributes to represent, they are all numbers, and you can use them position, color, or maybe size to represent them. And you want to all these 3 channels can work effectively without being affected or by the other channels being used. And in real life, for example, and if you have size and both size and color to represent, say, attributes, and you can imagine for very small marks, that means that for whatever attributes the size represents is very small, it might become harder to see the color. So they are not completely independent. Okay, and then so in terms of channels, and you can call them they are orthogonal or independent, and if they are completely separable in the sense changes in one channel does not affect the other. Or sometimes they are integral, that means 2 channels and cannot be easily separated. They almost look at human would treat them as one channel. Okay, and there's somewhere in between these 2. So there's completely separable and completely integrated or combined. And there's a spectrum somewhere in between. So halfway, for example, and somehow separable, but still kind of some integrated. Okay, we're going to see some examples later on, but obviously, and if they are separable, then it's okay. It's straightforward. You can easily use each channel to represent an attribute. And if you use integrated channels, and people would confuse whether that's one or just multiple channels. And then the more integrated the channels are, the more likely people will fail to see the values you want to show. Okay, so let's have a look at this example. Okay, and okay, so for this one, we're showing kind of dots in the visualization. So some dots are red, some dots are blue, but also there's kind of a group of dots on this side and group dots on the other side. Yeah. So what you can potentially say is that I can have two groupings, and one grouping is done by the position. I can see this is one of the groupings. Maybe that's one of the categorical value I want to present. For example, that's the location of the product. So all these are my Asian and product sold in Asian, and all these are the product sold in, say, Europe. So that's one grouping, which is represented by the position, which is one of the channels. And you can also say, okay, then I use color to represent the category of the product. So these red ones are the furnitures, and the blue ones are the ITs. So I can clearly see that separation as well. So I can see where all the IT product is and where all the furniture is. Yeah. So I would say these two are fully separable in the sense. So we have these two channels, position and the color, and they do not really interfere each other. We can clearly see position-wise how they are grouped and color-wise how they are grouped. Yeah. And even though I might say, and if you had to compare between the sense of grouping, I would say this is maybe like a stronger group compared to color-based, isn't it? So that's why, if you remember early on, position is the most effective channel for showing the categories, and the color is the one after. Okay, and let's look at this second examples. And can you see different groupings? Anyone?
No, Professor.
No, you cannot see any different groupings. So, or let's say the grouping by different visual channels. So it can be position, can be, say, color, size, lens, these kind of, or tilt levels. Can you see different groupings at all?
Colors are different.
Yeah.
And size also different.
Based on colors.
Yeah.
And based on size as well.
Yeah. Okay. So I think people already picked it. Actually, so also have at least two different visual channels, and one is the color. So you can see some dots are purple and the other ones are blue. So you can have one groups and just have the groups by colors, the purple group and the blue group. But also you can say the size are also different. And so you have these big circles and these small circles and maybe the medium as well. Okay, and so indeed we can try to show again two attributes, one use size, the other one using color, and they are still separable, but some interference. For example, you can imagine if it gets really small and the colors become difficult to see. Okay, and so this is the third examples. So how many different groups can you see? And for each grouping, how many different value you can see? Okay, so what you meant is, for example, here you can see two groupings, and one is by color, you have two values. The other is by size, you maybe have three values. So how many groupings can you see here?
So
Here shape,
size.
size,
Size and
shape and size only.
Okay,
Not
shape and
color.
size, yeah. And so I have someone says they can see two groupings. One is by shape, the other is by size.
Dimension.
Dimension? Did someone say? Okay, I'm not exactly sure what do you mean by dimension. So I assume it's something similar to the size. And here we, again, I just want to repeat, we have to use the different terms we used before. So
Shape.
So we have to use one of these, say position, lens, tilt, or color, or motion, or shape. Yeah, these are the ones we have to use. Anyone else? Any other? dimension,
area,
okay, yeah. I think the most common one is probably one is shape, the other one is size or area, and I think they more or less the same thing. Potentially dimension is also one of these, very similar. But actually what the people initially designed the visualization is actually they trying to use width and height. So they want to use the width of the marker to show one attribute, for example, the price, and then the height to show another value, for example, and how much did you sell, the number of products. Okay, but what actually you see is you actually see different types. You have the circles and the eclipse and then dots. Okay, so this is example. The width and height itself, or you can say they are two different visual channels, but they have more interference, and people might perceive them as just say one visual channel, which is a shape or size. Okay, and let's have a look at the last one. And can you see different? Okay, so maybe the first question is, can you see multiple groupings or just a single grouping?
Multiple.
Multiple.
Color.
single, multiple.
It's multiple.
Only color.
Yes,
Only
yes.
color.
So if you say only colors, that just means one way of group. And say
Yeah.
using colors, you might see multiple colors and you have multiple groups in color. And do you see any other way of grouping this besides color?
No.
No? Yeah. Okay. So what you might see is, okay, this is maybe grouped by color. You have this kind of purple and dark blue. Let's say this is pink, purple, and this light blue and gray. These are the four colors. You might see these are the four.
Professor, does will saturation come over here?
And
Because
saturation.
we have two colors in blue, right?
Ah, okay. Yeah, that can be one way. You can interpret is say it might be saturation could be a way, and maybe this purple and this kind of light blue, or this you call this dark blue and this light blue, that can potentially be one way to and another different channel. Okay. But actually what and they actually designed for is it used amount of red to show one value and the amount of green to show another value, like another attribute. Okay, but in the end you really can't really tell the difference in terms of red or green. You only just see different colors, that's all. Okay, so that means there's a major interference between these two channels, and as a result, and this is not separable at all. You cannot see this as two different ways of representing two different attributes. Whether you're seeing this is probably just representing one attribute using color. So we want to, so that's the thing, when you're choosing your attributes, sorry, your channels to represent your attributes, you want to make sure they are fully separable as much as you can, and avoiding the case like this, when the two channels are completely integrated and you can't really tell there are two different channels, but rather you will see as one. Okay, and the next one would be the pop-out effect. That's the last one to show different, to decide whether a channel is effective or not. And so this is just something we naturally do as a human. And for example, if you need to find the red dot among the blue ones, it takes almost no time, right? It's very quick. Just somehow, this is how our visual system works. We can pick out the red one very quickly. And just to give you another example, So again, if you do the same task, if you need to find this red dot among all the blue ones, again, it takes almost no time. Yeah, and this is actually the ideal case. So that means even you have more data points, you can still find the answer very quickly, actually regardless of how many data points are there. Okay, so that's the best possible case. So for the computers, even for the computers, if it needs to find a red dot among the blue dot, and can do this very quickly, but it have to go through all of them and find which one is red. And as you has more points, it will take longer time. And you can imagine this is maybe take twice or 3 times longer. Even overall is still very quick. And you can imagine if you have 1 million points and I want to pick the red one, the computer will take much longer, but we as human can almost do this instantly, still even though it has 1 million points, blue points. Okay, and can anyone see the odd one in this one?
Yes, Professor.
Circle. Circle.
There is a
The
circle dot.
yeah.
Yes, sir, there is a circle dot.
Yes, that's right. So we have all squares, but this one is circle. Okay, but maybe I would say this is slightly slower or more difficult compared to these two. Yeah, and then I will see this one. Can you see the
circle again.
Again dot.
yeah?
Again a circle.
Yeah, so it's the same thing. So it's just the case we can just add more squares and you can still see the circle here, but it's starting to getting harder. And okay, and this one, can anyone see the odd one?
Red
There's a
circle.
dot.
Red circle.
Yes, exactly. Okay,
Yes.
obviously just by say the time taking to getting the answers. So for these almost instantly, but this one will take maybe a few seconds, and people say, okay, the odd one is actually here. So it's a red circle. So, and the reason here, and one of the reason happens is because here we only change one channel. So this is only the color channel, and this is only the shape channel. So we can pick up very quickly or much faster. Whether here we have 2 channels, they both change. So both the color and the shape changes, so it takes a little bit longer. And how about this one? Can you find the odd one?
Red circle.
So
Yeah.
there's a
Red
Red circle.
There's a
Yes,
dot.
yes.
But
Yeah.
it still takes a certain time, Professor.
Yeah. So as you can see, and for this one, the odd one is still the red circle roughly here. And this, again, will take even longer than this. And so what happens is now, and what we so-called this pop-out effect is getting weaker and weaker. We almost have to go through the entire data set to find the odd one. And then in that sense, as the number of data points increases, it takes longer to find the item. Okay. And so what we want to do is we want to design the visualization like this way. And so we can pick out the patterns. Let's say that we want to find the outliers, and then we can find this one very quickly. And so once you're getting more complex, and it will becomes harder and harder to do, or takes longer time to do, and then that's something we want to kind of try to avoid. So we can make the visualization, so this will be the more effective one compared to this one. Okay, and there's many channels that has this effect. And usually it's the number of channels you use or changes affecting the pop-out effect. So for example, we can easily see this is a vertical one and everything else is an horizontal. Yeah. And you can see this one is a bit thicker in terms of size. Yeah. Shape is a,
Yes.
and this one, can anyone see the difference? So this one is a bit harder to see. So these ones are grouped closer together, whereas these ones are more spread out. So in terms, this one is a less obvious channel for the pop-out effect.
Professor, isn't
Yeah.
the differentiating factor in this one last one as well as like a position? Proximity is similar to position.
Yes, yes, yeah. Okay. Can anyone see which one is odd in here?
The ones which are single.
The triple circles.
The triple one, yeah.
The
One
triple
dot.
circles?
Triple circles.
Section of one
Yeah.
dot is also there.
The direction of shadows as well.
Yes,
I
group
think
of
the
triple
direction of
circles
shadow.
is odd one
It's up.
Section of shadow.
because all are in
Shadow
the
is
same
upward.
direction, but the triple circle is different.
Yeah, and but actually, and the answer is not this one, not in terms of proximity again. It's actually just this dot, and the direction of this shadow is different compared to the others.
Yes,
For the
yes.
old other points, the shadow is come to the lower right, and only for this one, it's up left. Okay, so obviously this is a
Yes.
something much harder to see in terms of the effects, the pop-out effect. And we're going to see one last one. Okay, which one is the odd one?
That just
There's one which is
The
parallel,
equal,
two
yeah.
parallel lines. Others are not parallel.
Yes, exactly. Yeah. Okay. So again, so this is take a bit longer time. So the odd one is here. So only these are parallel, whereas all the other ones are not parallel to pair. So these are the less and obvious channels for the pop-out effect. So we want to try to use these ones, which are obvious, and try to avoid these ones, which are less obvious. Okay, and last we want to show and some different channels in terms of representing group. So you want to say those things are in the same group. And hang on, give me a minute. I think. Okay, and I'm back. And so there's different ways you can show, and these are not exactly the channels that we've seen before. And so, for example, you can use containment to show a grouping. So you can draw a shape like this, including everything that is in the same group. Or you can use lines to connect the points that's in the same group. Okay, and you can use
containment is dot connection is
okay, and then you can also use proximity in terms of you put the things which are similar and next to each other. Okay, and the other things is just those things we list here. So you can always group things and by location, so put them next to each other besides these two. And these are just say different copied from previous slides in terms of categorical attributes from the most effective to the least effective ones.
Professor,
Yeah.
remember you just shown an example in the last slide itself where the grouping, the base on which we are going to group it was proximity. Is the motion over here similar to what you were implying over there, like the shadow and everything, like shadow part? That was the regarding the motion.
And I would say shadow is still different from motion. So motion is actually really, and some of the points, for example, will be static, don't move. And other points will be moving, like the ones have the circle, actually will be moving around. That's what the motion means, which I couldn't quite show, and because this is just a picture. Well, it's different from shadow. Shadow is just a different one.
Thank you, Professor.
And okay, let me just check how much time do we have left. Okay, and so we still have a little bit of time. So for up to now, we have covered and everything regarding to the channel. And then now there's some other general rules, and that might help you in terms of visualization design. And again, these are called rules of thumbs in the sense they are just advice and guidelines. They are not 100% correct. They are not strict. Yeah. So you need to adapt. It depends on your visualization and your tasks. And so these are kind of extracted from like a very recent research, and because data validation itself is still a relatively young research field, and it only has maybe started in the 1990s as an independent field, and there's still lots of questions we haven't had like a very clear answer yet. And these actually may change or update as people doing more research and discover more things. Okay, and then so the first rule, it says no unjustified 3D. And so if two dimension, so some people might think 3D is always good. If two dimensions are good, 3 dimensions must be better. And so for example, you can show this kind of 3D networks in 3D spaces. And but actually, and so first, the depth and is something not very effective if we want to use that to encoding attributes. And we already said XY position is actually quite good, but depth is much less so. And then, so it is easy, say, to use a 3D validation if the data is 3D. So for example, we've seen these examples before, and these are a 3D scan of the human brain. And because the data is 3D and using a 3D visualizations make it much easier compared to 2D ones. And this is some other visualizations I did before try to using 3D and showing a network below, and then using the 3D shapes to show the different values. For example, each point has 2 values. One is showing you with the blue, the other one is showing with the red color surface. Okay, and if the data itself is not 3D, and you need to be very careful, and because 2D dimension my work turned out to be a better visual representation. And as we already said before, it's not about how fancy the visualization is, it's about how effective it is in showing the data. So the problem with the 3D, you can have potential occlusion. In the sense, something in the 3D visualization may block something behind, and you might have perspective distortion in the things further away will look smaller, even they are the same size, but they're seeing smaller 3D visualization and some other issues. Okay, and so first, and quickly review, again, this is the list that we had before, and we can see, and the depth of position is quite low down and in the effective list. So basically, people did experiment, find out, and it's not very good at showing values, or people cannot perceive it accurately. Okay, and then this is again the same chart we've seen before. You can see that's where the depth is, and the green line here. So usually people would underestimate the changes with depths. Okay, and then this is the examples when occlusion can potentially happen. So again, we are showing a network, but this applies to other data sets as well. And then say the things front obviously stops block the things from behind which you can't see and make it harder to see the data. But actually, and the occlusion is actually important for 3D visualization as well. So this is actually how we as a human to perceive which one is closer, because the one and in the front will be perceived as closer to you, and the one further away or behind will be perceived as the one being blocked will be perceived as further away from you. So it's actually important for us to perceive depth occlusion, even though it hides some information or blocks some information from us. Okay, and this is actually can improve, and if the user allowed to interact with the visualization. For example, if you can rotating this visualization around, then the occlusion becomes much less a problem. But also, as we rotating, our perception of the depths also improves as well. So interactive navigation, so as a result, is critical for visualization, for 3D visualization. So if I this site is gone. No. Okay. So it's actually there's a link goes to an online website which allows you to show this picture which you can interact with, but that's gone now. Okay. And so the disadvantage is says some things might be blocked and you have to turn the things around to check it. Okay. And finally, and this is about 3D, and we talked about one of the problem is about the perspective distortion. So the things will appear smaller when it's further away from you. So we all seeing this, probably think we as human would see this. If each of these is in data points, and these are 3D, and these ones further away from you and look smaller, and they're also closer to each other, but we probably would still perceive they are still parallel lines. For these lines, they are parallel. Yeah, but obviously this can be difficult, and when you try to do, okay, so one difficulty is might interfere with other visual encoding. So because for these ones, and this is further away from you, it becomes smaller and it becomes harder to tell, for example, the size or the shape of the marker. Okay, and this is another example. So this is showing the same data, this done in 3D and this done in 2D. So this is like the 3D bar chart. And you can have the typical problems, for example, and you have these little ones being blocked by the one in front. And also, it's not necessarily easier to compare either when it's 3D. Let me see. Okay, and so I'm not sure if you can see clearly. So here, let's say this is the x-axis. Let's say it shows different categories: payroll, equipment, travel. So that's along here. So you can clearly see for the last one and the pink one, which is being blocked, you can see the values clearly. And also in terms of comparing the values, for example, the green one here might be a little bit difficult to see, whereas using the 2D bar chart, the difference between the different bars is actually, the difference is actually easier to see compared to this one. And I guess the only downside I would say, maybe say for this one, it would take more space to display compared to this one. That's probably the only downside. Otherwise, in terms, will be a more effective validation because it's easier, there's no occlusion, and easier to compare between the different values. Okay, so all are we saying up to here, it says don't use 3D unless there's a very good reason for it. So it could just be, say, the data itself is a 3D model, then you have to. Whereas, I mean, in our case, it's actually a very limited case like that. And that's also a reason, I don't know if it's true, but I think it might be a reason why, for example, in Tableau, you cannot even do 3D. They don't even provide 3D capabilities for visualization. Whereas, for example, even in Microsoft Excel spreadsheet, you can do 3D bar charts. So it's technically not that difficult to do. But Tableau decided, I think, not to do it because it's known to be not very good. And okay, how we are doing time? Yeah. And so the next one, it says an I-space memory. And so we as humans actually are not very good at remembering things. And that's one of the reasons actually we're using visualization, so we can show all the data and information, so we don't have to hold it in our memory, try to remember them. Okay, and then, so one type of visualization is about dynamic visualization. So where you show the data, the changes over time, and it's easier to, one way to show these dynamic information, one is to show an animation to see how the things change over time. And the other one is to show a state at different states and show many of these states at the same time. Okay, then for the animation one, you have to remember everything in your mind. And whereas if you show all the states at the same time, you don't have to, so make that easier. So I'm gonna show you an example here. Hopefully this one would work, or at least still works. Yeah. Okay, so this is a visualization, oops, and of the flight between the Europe and the US. And can you see my screen okay?
Yes, Professor.
Yeah,
Yes,
okay.
Professor.
So what it shows is, I think each line, so each little dot is a flight or plane. And it just shows how the flight happening. Obviously, this is before COVID and mostly between the Europe and US. So this is the time, and you can see that's early in the morning, starts coming from the America to the Europe, and obviously lots of flights within the Europe as well. As it becomes busier, it becomes lighter, brighter. Okay, now it moves to the time between 9 and 12. Okay, so this is a flight within the UK 10, okay. Okay, and if you're interested, you can watch the video yourself, and the link is in the slides. If you just click on the picture itself, we should go into the go to the actual video. Okay, so the question here is, so certainly it looks very nice, it's very well designed, looks very interesting, everything is moving. But let's say we roughly stop to here, it's between 10 and 1, that's about flight in the UK. And what if I ask you what the flight was like before 9 o'clock in the Europe? Did anyone remember that?
No, Professor.
Yeah. So that's the thing. So we as human is not very good at remember these things. Okay. So when we look at it when we're looking at it, we can see the patterns. For example, now we can see what is happening in the UK roughly at that time. But if we had to remember what happened before, we are not very good at all. Okay, so these animations are good for telling the stories, and it's quite interesting and quite interesting to show the transitions between different states. But if you have many things and you have to remember, most likely people, you have to go back to the video just to understand exactly what is happening at different times. Okay, and the alternatives is just to create multiple visualizations of different time points. Let's assume that's the network at, say, 5 o'clock, 6 o'clock, 7, 8, 9, etc., etc. And this way, and it's actually much easier for us as human to understand. And this particular method is called small multiples. And so you show multiple copies of the similar data, but usually at different states, slightly changes between these. And okay, so this is another guideline. It says resolution beats immersion. And so it is mostly about these new type of display device, and either VR or AR. And they are very immersive in the sense, if you put it on, you feel more like, you still know it's not real, but you feel much more likely to be there. So the immersion is much stronger with these type of displays, and might be useful. But the disadvantage of this type of display is you have to do the same image of visualization twice, one for the left eye, the other for the right eye, with tiny differences. So when the user sees it, it will have a feeling of being 3D, real and more realistic 3D, let's say. But as a downside, that means you only have half of your display space to show the information, because the other half have to be used to almost replicate exactly the same information with slightly differences, or you can't really include any new information in the other half. Okay, so that means, I think if you remember, maybe in the first lecture we talked about, and the amount of this display space is very important factor when we do the visualization, sometimes limiting, depends on how much data you can see, you can show. Okay, so using these VR or AR can potentially half the amount of space you can use to display information. So you have to be very careful. And if that's a trade-off you want to do, so if in the case where showing more information is more important than, say, feel realistic, then you should not using these type of display. Okay, but there's other things maybe it's important. For example, you have to be there, be able to interact with it naturally, be able to understand the data. Then maybe those are the cases where, say, VR or AR, virtual reality or augmented reality, is justified. Okay, and this is another guideline, but this time is actually not a negative, like some things you want to avoid, but something you want to probably follow, and is the general rules for visualizing a large amount of data. It's called an overview first, zoom and filter, and finally details on demand. And so when you have lots of data and you want to give users an overview, so they know where they are looking at in terms of the entire data set. So use this Google map as examples. So this gives you the overview of the entire map, and it shows, okay, this is the part of the map you're currently looking at, which is shown as here. And you would allow user to zoom and filter, and so for in this case, and user picked a particular region of the map, so that's the equivalent of filtering, and you're doing the zooming, change different display levels, you can see, so you can see more details. And finally, details on demand. And even this is a more detailed view than the entire overview, but still there's lots of information being hidden from the user. And for example, if you want to know the details about particularly place, and the user usually would have to click on the city, for example, Detroit or Toronto, and then Google Map would and provide more details about that particular place. And that's what is called details on command. Okay, so that's the general way of using how do you visualize lots of information when the items are not possible to fit on the entire screen, and you try to provide an overview, and which itself has to be overly simplified or aggregated. You can't see lots of details. And you allow user to zoom and filter, basically select the part of the data set and providing more details about that part. And for the very detailed information, and you want it done through user interaction, so that user needs to either select something or turn on a switch or a button and to show the particular details of an items in the data set. So that seems to be a very effective, a successful strategy for visualizing very large data sets. Okay, and I guess as we talked so far, a good visualization should achieve and to show the information effectively. That's the most important thing. And how beautiful or how colorful or how fancy it looks should come next. Okay, and so at least for the book, the author of the book, she recommends we should focus on the functionality. Okay, and one of the arguments is says if you is effective and it's easier to improve the design later on as refinement. And but if you start with the how good looking that is, and it's quite difficult to change the design later on to make it effective. Okay, and again, just say so we're showing this picture again in the sense, and you want to explore and lots of options early on to find the most effective ones, then you're more likely to find the effective one. And if you start with a very small collections of options, and you might find the best one within your available options, but that might not be the best option overall because you're missing many other options you didn't explore. Okay, and so visual design or beauty or form actually is quite important as well. And so in real world, people probably usually prefer and better form. And so if you give people two pictures, one in 2D, one in 3D, without any other information, and they have to pick which one they like better, they might still pick the 2D one, sorry, the 3D one. Or you give two versions, one is more colorful than the other, and without any other information, people might just still pick the more colorful one. Okay. And also, and so this is in terms of important, in terms of engaging. So sometimes the first task your visualization need to do is get people's attention, and before it can becomes effective. So if people don't even want to look at the visualization, and then even if it's very effective, then that's not working very well, and it's not going to achieve its goal at all. Then you have to say, think about how do you balance between how attractive your visualization is and how effective that is. Okay, and also there's some studies showing saying, and if you have good visual design, it actually improves the effectiveness of the visual representation as well. So it's not just saying attracting people, it can actually improve effectiveness to a certain extent. Okay, and so that's it. And we finally finished the lecture. So in terms of the reading, so that's for actually both this week and the last week, and will be the chapter 5 and 6 of the book. So the chapter 5 talks about the markers and channels, and the chapter 6 talks about the rules of sums, which will cover the general guidelines design, the things you should avoid, and the things you should follow when you design a visualization. Okay, that's it.
Thank you, Professor.
Okay, thank you.
Thank you, Professor.